Henry Ford was furious. The story begins with a grudge, a rejected contract, and the most productive act of spite in American industrial history. In 1940, as war consumed Europe, the British government desperately needed American factories to produce Rolls-Royce Merlin engines, the superb V12 that powered the Spitfire and the Hurricane. Rolls-Royce approached Packard, the American luxury car manufacturer, to negotiate a licensed production agreement. Henry Ford was also approached, or, depending on which account you believe, approached himself. Ford wanted the Merlin contract badly. His company had produced the Liberty V12 aircraft engine during the First World War, over 10,000 of them, at the same Lincoln plant that would later build the GAA. Ford understood aircraft engine production. He had the factory, he had the workforce, he had the institutional memory. But negotiations collapsed. The details are disputed. Some accounts say Ford insisted on modifications to the Merlin design to make it more suitable for mass production, and Rolls-Royce refused to alter their blueprints. Others say Ford's well-known isolationist politics, he had publicly opposed American involvement in European wars, made the British government uncomfortable. Whatever the reason, the Merlin contract went to Packard. Ford was left with nothing. Henry Ford did not accept rejection gracefully. He instructed his best engineers to design a V12 that would not merely match the Merlin, but surpass it. If Rolls-Royce would not let Ford build their engine, Ford would build a better one. The result was a 27-liter V12, all aluminum, dual overhead cams, 4 valves per cylinder, designed from the ground up to outperform the Rolls-Royce Merlin. The Merlin was the engine that powered the Spitfire, the Hurricane, the Lancaster, the engine that had saved Britain during the Battle of Britain. Ford wanted to build something better. The V12 was a masterpiece of engineering. It was lighter than the Merlin. It was designed for high-volume production. Ford knew how to mass-produce things that Rolls-Royce built by hand. It featured innovations that would not appear in civilian engines for another 60 years. Dual overhead camshafts, 4 valves per cylinder, gear-driven accessories with no belts or chains to break, centrally located spark plugs for optimal combustion. In every measurable way, it was a generation ahead of anything in the sky. The Army Air Corps rejected it. They had already committed to the Allison V-1710 for their fighters, and Packard was licensed to produce the Merlin. There was no room in the procurement pipeline for a third liquid-cooled V12, no matter how good it was. Ford had spent millions developing an engine that nobody wanted. What happened next is one of the great accidental triumphs of American industrial engineering. The Army did not need another aircraft V12, but the Army desperately needed a tank engine, a V8 specifically, to power the M4 Sherman, the medium tank that was about to become the backbone of every Allied armored force from North Africa to Berlin. Ford's engineers looked at their rejected V12. They looked at the tooling. They looked at the casting cores, and they did something that only an American automobile company in 1942 would have the audacity to do. They cut 4 cylinders off the back of a 27-liter aircraft engine and turned it into an 18-liter tank motor. The result was the Ford GAA, 1,100 cubic inches, 500 horsepower, 1,050 pound-feet of torque, all aluminum, dual overhead cams, 32 valves, gear-driven everything. The largest gasoline-powered all-aluminum V8 ever built. The engine that powered the Sherman tank to victory. The engine that 80 years later shares more DNA with the V8 in a modern Ford Shelby GT350 than most people realize. This is the story of an engine that was born for the sky, rejected by the Air Force, adopted by the Army, and went on to become the most reliable tank power plant of the Second World War, built nearly 27,000 times at Ford's Lincoln plant in Detroit, installed in every variant of the Sherman that the United States Army kept for itself. To understand why the Ford GAA mattered, you need to understand what the Sherman was running on before it arrived. The original M4 Sherman was powered by the Continental R975, a 9-cylinder air-cooled radial engine. This was, in essence, an aircraft engine designed in the 1920s, a licensed-built version of the Wright R975 Whirlwind, manufactured by Continental for ground use. It produced 400 horsepower in its best variants and had the approximate dimensions and shape of a large barrel, round, tall, and wide. It took up an absurd amount of space inside a tank hull, and its air cooling system required enormous ducting that further reduced the available interior volume. The engine sat high in the hull, forcing the Sherman's distinctive tall silhouette, a profile that made it easier for German gunners to hit. Why was an aircraft engine in a tank? The answer is a story of peacetime neglect. Between the wars, the United States Army had spent virtually nothing on armored vehicle development. The total budget for tank research and development in the 1930s was so small that the Army could not afford to commission a purpose-built tank engine. When the M3 Lee and then the M4 Sherman entered production, the Ordnance Department reached for whatever engine was available in quantity. The R975 was available because Continental had been building it for civilian aircraft for years. It was proven, it was in production. It was the wrong engine for a tank, but it was the engine they had. Continental would eventually produce over 53,000 R975 engines for tank use, more than Wright had ever built for aviation. The engine was adequate. It was never good. And as the Sherman gained weight with each modification, thicker armor after encounters with German 75mm and 88mm guns, heavier turrets to accommodate the 76mm gun, additional ammunition storage, the R975's 400 horsepower became increasingly marginal. A 35-ton tank running on 400 horsepower has a power-to-weight ratio of approximately 11.4 horsepower per ton. A Panther at 45 tons with 700 horsepower had 15.6. The numbers mattered in the field, in acceleration out of cover, in the ability to climb a muddy hill, in the speed to cross an open field before an anti-tank gun could traverse. The Army knew it needed alternatives. It went to the American automobile industry, General Motors, Chrysler, and Ford, and said, in effect, "Build us a tank engine, now." General Motors responded first. Their answer was the GM 6046, a pair of GMC 6-71 inline six-cylinder diesel engines, the same motors that powered city buses, bolted together and mated to a common transmission. It was unglamorous, reliable, and produced about 375 horsepower. The Marine Corps liked it because diesel fuel was less flammable than gasoline, a critical consideration when tanks were being loaded onto ships. The Army was less enthusiastic. Chrysler's solution was stranger. The A57 Multibank was literally 5 inline six-cylinder flathead automobile engines, 5 of them bolted to a common crankcase and driving a single output shaft. 30 cylinders, 5 distributors, 5 sets of spark plugs. The maintenance nightmare was predictable. Servicing a 30-cylinder engine in a field workshop was a proposition that made seasoned mechanics weep. The A57 produced only 370 horsepower, less than the R975 it was supposed to replace, and the complexity of the installation created reliability problems that took months to resolve. The Army did not like either of these engines. They were expedient solutions, lash-ups in engineering terminology, that solved the immediate production problem but did not address the fundamental need for a purpose-designed, high-performance tank power plant. If the British had not been willing to accept the A57-powered M4A4 variant, the Army would have relegated those tanks to training use only. What the Army wanted was a modern, powerful, reliable V8, an engine designed with the same engineering sophistication as the best aircraft engines, but optimized for the specific demands of armored warfare: high torque at low RPM, extreme durability, resistance to dust and debris, and the ability to run for hundreds of hours between overhauls. Ford had exactly that engine. They had just cut 4 cylinders off it. The Ford GAA, the designation stood for G-Series, A-Type, A model, was born from the rejected V12 in a way that seems almost too convenient to be true. Ford's engineers took the existing V12 design with all its advanced features and simply removed the rear four cylinders. The 60-degree bank angle of the V12 was retained, which is why the GAA is a 60-degree V8 rather than the 90-degree configuration typical of most American V8s. The bore and stroke remained the same, 5.4 inches by 6 inches. The displacement dropped from approximately 1,650 cubic inches in V12 form to 1,100 cubic inches as a V8. The existing tooling, casting cores, and production fixtures required only minor modification. The result was, by any standard, an extraordinary engine. The block was a one-piece casting in aluminum, not the cast iron used in virtually every other tank engine of the era. This made the GAA remarkably light for its displacement, approximately 1,560 pounds dry, compared to over 2,000 pounds for the comparable German Maybach HL230. The heads were aluminum, with hemispherical combustion chambers and centrally located spark plugs, a configuration that would not become standard in automobile engines until the 1990s. The Trine valve train was true dual overhead cam, 2 camshafts per head, 4 per engine, each acting directly on bucket followers with no intermediate rocker arms. 4 valves per cylinder, 2 intake, 2 exhaust, provided the breathing capacity needed for high power output. The entire valve train and all accessories, generators, fuel pumps, water pumps, magnetos, distributors, were driven by gears and shafts. There were no belts, there were no chains, nothing to stretch, wear, or break. In a tank engine that might run for hundreds of hours in combat conditions, this was not a luxury, it was a necessity. The ignition system was dual magnetos with twin spark plugs per cylinder, a full dual ignition system so that the engine would continue to run even if one complete ignition system failed. This was aircraft engine thinking applied to a ground vehicle, and it reflected the GAA's origins as a descendant of the V12 aviation design. The crankshaft was a flat plane design, meaning the crank throws were spaced at 180 degrees rather than the 90 degrees typical of most V8s. This produced a distinctive firing order and exhaust note, and it provided more uniform power delivery at the low RPM ranges where a tank engine operates. The flat plane crank is the same configuration used in the Ford Shelby GT350's Voodoo engine, introduced in 2016, 74 years after the GAA. Ford's marketing department celebrated the Voodoo's flat plane crank as a technological breakthrough. It was, in fact, a return to a design that Ford had already mastered in 1942. The power output was 500 horsepower at 2,600 RPM, gross, making it the most powerful engine ever installed in a Sherman tank. But the truly remarkable number was the torque, 1,050 pound-feet at 2,200 RPM, with 90% of peak torque available from just 1,000 RPM. For a 35-ton tank that needed to climb hills, cross trenches, and push through mud, low-end torque was everything. The GAA delivered it in overwhelming quantity. A 198-pound flywheel smoothed the power delivery. The compression ratio was 7.5 to 1, moderate by aircraft standards, but appropriate for 80-octane motor fuel. The engine consumed approximately 32 quarts of oil. It was fed by twin Stromberg carburetors. It was enormous by automobile standards, nearly 5 feet long and 3 feet wide, but it fit into the Sherman's engine bay with room for maintenance access. Ford produced the GAA and its variants at the Lincoln plant on Warren Avenue on the west side of Detroit. This was poetically appropriate. The Lincoln factory had been built by Henry and Wilfred Leland specifically to produce Liberty V12 aircraft engines during the First World War. The Lelands, who had founded Lincoln Motor Company for exactly this purpose, after leaving Cadillac because William Durant was not sufficiently committed to the war effort, produced thousands of Liberty engines at this facility between 1917 and 1918. Henry Ford acquired Lincoln in 1922 and converted the factory to automobile production. Now, 20 years later, the factory was building another V engine for another war. The ghosts of the Liberty V12 watched over the production line that built its spiritual descendant. Production began in 1942. The scale-up was rapid. Ford's mass production expertise, the assembly line methodology that Henry Ford had pioneered in the Highland Park plant in 1913, was applied to an engine of aircraft-level complexity. Each GAA required precision machining of its aluminum block, heads, and internal components to tolerances that were tighter than any automobile engine of the era. The dual overhead cam assemblies, the gear-driven accessory drives, the dual magneto-ignition system all required the kind of attention to detail that was more typical of an aircraft engine shop than an automobile factory. But Ford was not building aircraft. Ford was building engines at automobile industry volume. The company applied its institutional knowledge of high-volume production to an engine that would have been considered a boutique product by any other manufacturer. Jigs, fixtures, and quality control procedures were designed to maintain aircraft-level precision at automobile-level output. The result was an engine that combined the engineering sophistication of a Rolls-Royce Merlin with the production accessibility of a Ford Flathead. During the war, Ford's Lincoln plant produced 26,954 GAA V8 engines. Including the GAF variant used in the M26 Pershing heavy tank, the GAN and other derivatives, total production exceeded 28,000 units. Of these, approximately 14,000 were factory-installed in new Sherman tanks at two primary locations, the Chrysler Tank Arsenal in Warren, Michigan, and Fisher Body's Grand Blanc Tank Arsenal in Flint, Michigan. The relationship between these three companies was a uniquely American arrangement. Ford built the engines, Chrysler and Fisher built the tanks. The companies were fierce commercial rivals in the automobile market. Ford, GM, Fisher's parent, and Chrysler competed for every customer in every showroom in America. But in wartime, they cooperated seamlessly. Ford engines were shipped from the Lincoln plant to Chrysler's arsenal, where Chrysler workers installed them in Chrysler-built hulls, equipped with guns from Oldsmobile, transmissions from GM's other divisions, and optics from yet another supplier. The competitive instincts that drove the American automobile industry in peacetime were channeled into a collaborative production system that outproduced every other nation on Earth. Chrysler alone produced 17,947 Sherman tanks. Fisher produced 11,558. Together with Ford's 1,690 and contributions from other manufacturers, Pressed Steel Car, Pullman Standard, American Locomotive, Pacific Car and Foundry, Baldwin Locomotive, Federal Machine and Welder, and the Montreal Locomotive Works in Canada, the total Sherman production exceeded 49,000 tanks. The GAA-powered M4A3 variants represented the Army's preferred configuration, and by war's end, it was the only Sherman variant the Army intended to keep in service. Ford itself stopped building complete tanks in September 1943 after producing its 1,690 M4A3s at the Highland Park facility. But the company continued to supply engines to Chrysler and Fisher for the remainder of the war and beyond. Ford also produced 1,038 M10A1 Wolverine tank destroyers. The company's primary wartime achievement, however, was not in final assembly. It was in the engine that made the best Sherman the best Sherman. Ford was simultaneously building B-24 Liberator bombers at the enormous Willow Run plant, a production miracle in its own right, eventually producing one B-24 every 63 minutes. The GAA engine program received less public attention than Willow Run, but its impact on the ground war was arguably greater. Every B-24 contributed to the air campaign. Every GAA engine contributed to the armored force that broke through the Siegfried Line, crossed the Rhine, and drove into the heart of Germany. To understand how good the Ford GAA was, compare it to its German counterpart. The Maybach HL230P30 was the standard engine for the Panther medium tank and the Tiger I heavy tank, the two most feared German armored vehicles of the war. It was a 23-liter, 60-degree V12, producing approximately 700 horsepower. On paper, it was more powerful than the GAA. In practice, it was an engineering cautionary tale. The Maybach was made of cast iron, not aluminum. It weighed over 2,700 pounds, nearly twice the GAA's weight, for only 40% more horsepower. It used a single overhead cam design with 2 valves per cylinder, technologically a generation behind the GAA's DOHC 4-valve layout. The cooling system was chronically inadequate, particularly in the 57-ton Tiger, where the engine bay generated heat that the radiators could not dissipate. Sustained operation at high RPM caused gasket failures. The crankshaft bearings were prone to premature wear. Head gasket failures occurred with dispiriting regularity, and a head gasket failure in a combat zone meant days of repair work, if the spare parts could be found at all. German tank crews developed an intimate adversarial relationship with their Maybach engines. They learned to listen for the sounds of impending failure, a subtle change in exhaust note, a rhythmic knock that signaled a bearing on its way out. They limited engine RPM whenever possible, avoiding the upper power band where the Maybach was most likely to self-destruct. They nursed their engines like fragile patients, and they still lost tanks to mechanical failure at a rate that horrified German logistics officers. The American experience was different. Tankers who drove GAA-powered M4A3 Shermans described the engine as virtually indestructible under normal combat conditions. It ran cool. It started reliably in cold weather, a critical advantage during the winter of 1944-1945 in the Ardennes, where temperatures dropped below -20 degrees Celsius. It tolerated dust, mud, and the terrible fuel quality that was sometimes the only option in forward areas. And when it did need maintenance, the all-aluminum construction and accessible design made field repairs faster than on any competing engine.
The GAA-powered M4A3 Sherman achieved an average engine life of 255 hours in the Army's standardized reliability tests, the best of any Sherman variant. The R975-powered M4A1 managed 218 hours. The Chrysler A57-powered M4A4 achieved 240 hours, but required far more maintenance time per hour of operation. The GM diesel M4A2 reached 225 hours. The Maybach HL230, by comparison, was considered to have reached the end of its operational life after approximately 150 hours in the Panther and considerably less in the heavier Tiger, where thermal stress accelerated wear. German tank crews learned to nurse their engines, avoiding sustained high RPM and limiting off-road operation whenever possible. American tank crews, by contrast, could run their GAA-powered Shermans hard and expect the engine to survive. This disparity in reliability had strategic consequences that shapes the outcome of the war. A tank with an unreliable engine is not merely inconvenient, it is a strategic liability. Every breakdown requires a recovery vehicle, itself consuming fuel and crew that could be used elsewhere. It requires a maintenance crew with specialized tools and spare parts. It requires hours or days of repair time during which the tank sits immobile, vulnerable to air attack and artillery. And it requires a supply chain that can deliver engine parts to a forward repair area, competing for road and rail space with ammunition, food, and fuel. The German armored forces of 1944-1945 lost as many tanks to mechanical failure as to enemy action. This is not hyperbole, it is documented in German after-action reports and logistics records. Panthers broke down on the road marches to the front.
Tigers consumed so much fuel and required so much maintenance that their operational availability, the percentage of vehicles ready to fight at any given moment, rarely exceeded 50%. The magnificent German armor that terrified Allied tankers was, from a logistics perspective, consuming itself. The American armored forces did not have this problem, or at least not to the same degree. The M4A3 Sherman, powered by the Ford GAA, had the highest operational availability of any American tank variant. It could march further on a single engine fill than any other Sherman. It could be maintained by crews with standard automotive tools, and the Ford GAA was a major reason why. When military historians analyze the Allied victory in the armored battles of 1944-1945, they focus on numbers. The Allies had more tanks. This is true, but they also had tanks that worked, and the engine that made them work was the GAA. The first GAA-powered Shermans, the M4A3 variant, were assembled in May 1942, but the engine was new and untested. The Army initially authorized M4A3s only for use as training tanks within the United States, giving Ford engineers time to resolve early production issues. By June 1943, after extensive testing, the GAA was declared superior to any other medium tank power plant now available. The Army's recommendation was unambiguous: build a pool of M4A3 tanks in all theaters and replace the R975-powered M4A1 with the M4A3 as fast as supply permits. An additional recommendation was even more telling: reserve Ford-powered combat vehicles for United States troops. The Army was keeping the best engine for itself. Lend-Lease Shermans, the thousands sent to Britain, the Soviet Union, and other allies, were primarily R975, GM diesel, or Chrysler A57 variants. The GAA-powered M4A3 was reserved for American tank battalions. This was not stated publicly for diplomatic reasons, but it was policy. The M4A3 saw combat in every theater from 1943 onward. It was the engine in the M4A3 75W, the workhorse of American armored divisions in France, Belgium, and Germany. It was the engine in the M4A3 76W, the upgun variant with the high-velocity 76mm gun that could engage Panthers at combat range. It was the engine in the M4A3 E2 Jumbo, the heavily armored assault variant used to break through fortified positions. And it was the engine in the M4A3 E8 Easy 8, the final production Sherman with horizontal volute suspension and the 76mm gun, the tank that would serve with the U.S. Army through the Korean War and beyond. The Easy 8 became the definitive Sherman, the version that every tank enthusiast pictures when they hear the name. It was fast, reliable, well-armed for its weight class, and powered by an engine that its crews trusted with their lives. The M4A3 E8 fought in Korea from 1950 to 1953, facing North Korean T-34-85s in battles where the Ford GAA's reliability was tested once again in freezing mountain conditions. The engine that had been designed for the sky, rejected, reborn, and proven in Europe, performed flawlessly in Korea, 10 years after its first production run, in conditions as harsh as any it had faced in the Ardennes. Israel operated GAA-powered Shermans into the 1970s, modifying them extensively with French and British guns and redesigned turrets. The engine outlasted multiple generations of the vehicle it powered. The GAA also powered the M10A1 Wolverine tank destroyer, the M7B1 Priest self-propelled howitzer, and eventually the M26 Pershing heavy tank that entered service in the final months of the European War. In reliability tests during 1943 and 1944, 10 M4A3 tanks covered a combined 20,346 miles, half on-road, half off-road, over 2,388 hours. The engines that were disqualified from the test were found to need only a single part replacement before returning to service. One tank covered 2,097 miles in 203 hours without a major breakdown. This was not the performance of an improvised wartime engine. This was the performance of a supremely well-engineered machine operating well within its design limits. When the fighting stopped, the Army kept its GAA-powered Shermans and let the rest go. The M4A3 76W was the standard post-war Sherman. Over time, as many as possible were converted to HVSS, horizontal volute spring suspension, creating the M4A3E8 configuration that would serve in Korea. The Army even swapped turrets between variants, taking 76mm turrets from M4A1s and installing them on M4A3 hulls solely to retain the Ford engine. Thousands of surplus GAA engines entered the civilian market. Their extreme reliability and low RPM torque made them ideal for industrial applications: oil field pumps, irrigation systems, logging equipment, marine propulsion. In Texas, farmers ran GAA engines on irrigation pumps non-stop for months at a time and recalled that they were as reliable as anything they had ever used. Then the hot rodders found them. The GAA's untapped potential was enormous. At 500 horsepower and 7.5-to-1 compression, the engine was loafing. Stock pistons were good to approximately 1,200 horsepower before the rings began to fail. With modern pistons, balanced rotating assemblies, fuel injection, and turbocharging, the GAA could produce 2,200 horsepower reliably. In one documented case in Brazil, a modified GAA with computerized ignition, fuel injection, and twin turbochargers produced 1,500 horsepower at just 8 pounds of boost, with the potential for 3,000 horsepower at higher boost levels. A GAA has been installed in a Ford Crown Victoria tube chassis streetcar. Another powers a Bonneville salt flat racer built from a belly tank. Art Arfonts, the legendary speed record holder, used a GAA in one of his land speed vehicles. The engine that was designed to fly, rejected by the Air Force, cut down to a V8 and installed in a tank, found its third life in the most American of settings: the drag strip and the salt flats.
Here is the connection that the title promises. The Ford GAA was a DOHC, 4-valve per cylinder, flat plane crank V8 with an aluminum block and gear-driven accessories. It was built in 1942. The Ford Shelby GT350's Voodoo engine, introduced in 2016, 74 years later, is a DOHC, 4-valve per cylinder, flat plane crank V8 with an aluminum block. When Ford's marketing department unveiled the Voodoo as a technological breakthrough, they were describing an architecture that Ford had already built in a tank factory during the Second World War. The modern F-150's 5-liter Coyote V8 is a DOHC, 4-valve per cylinder, with an aluminum block. The architecture is different in detail. The Coyote is a 90-degree V8 with a cross-plane crank, but the fundamental engineering philosophy is the same: aluminum for lightweight, dual overhead cams for breathing efficiency, 4 valves per cylinder for power density. Ford did not invent these ideas in 2011. Ford invented them in 1942. The GAA was 80 years ahead of its time, or, more accurately, the civilian automobile industry took 80 years to adopt the engineering that Ford had already proven in a tank engine during the war. The connection is not metaphorical, it is metallurgical. The same engineering principles, aluminum construction, overhead cam valve trains, multi-valve heads, and centrally located spark plugs flow in a direct line from the Lincoln plant on Warren Avenue in 1942 to the engine plants of Dearborn and Romeo today. The Ford V8 that powers the truck in your driveway is the grandchild of the Ford V8 that powered the Sherman to Berlin.
26,954 GAA engines produced at the Lincoln plant, over 28,000 including variants, 14,000 factory installed in new Sherman tanks, the rest retrofitted into existing vehicles or held as spares. 500 horsepower, 1,050 pound-feet of torque, 1,100 cubic inches, 32 valves, 4 cams, 0 belts, 0 chains, all aluminum, all gear-driven. The largest gasoline-powered all-aluminum V8 ever built. 255 hours mean time between failures, the best reliability of any Sherman variant. 20,346 miles covered in testing by 10 tanks, one engine that needed a single part replaced to return to service. And one angry industrialist who designed a V-12 to fly, had it rejected by the Air Force, cut 4 cylinders off it, and accidentally created the finest tank engine of the Second World War. Henry Ford wanted to beat Rolls-Royce. He failed at that, but in failing, he built something that Rolls-Royce's own tank engine, the Meteor, derived from the Merlin, could not match in reliability or production volume. The Meteor was a brilliant adaptation of a brilliant aircraft engine. The GAA was an accidental masterpiece, a rejected airplane motor that turned out to be the perfect heart for a tank. The Sherman was not the best tank of the war. It was not the most heavily armored or the most heavily gunned or the most feared, but it was the most produced, the most reliable, and the most available. And the version that the United States Army kept for itself, the M4A3, powered by the Ford GAA, was the best of them all. The engine in your truck descends from the engine that won the war. The engineering is the same. The ambition is the same. The flat plane crank, the overhead cams, the aluminum block, they were proven not on a racetrack or in a laboratory, but in the mud and fire and frozen forests of Europe, in a 35-ton machine that had to start every morning and run all day and not break down, because breaking down meant dying. The Ford GAA did not break down. It ran, and it is still running, in museums, in restored Shermans, in hot rods, in tractor pulls, in the genetic code of every Ford V8 built since. 1,100 cubic inches, the biggest Ford V8 ever built, and it started as an airplane engine that nobody wanted.
Here is what the Ford GAA teaches about war and engineering. It teaches that the best weapons are often accidents. The GAA was not designed to power a tank, it was designed to fly. When the sky rejected it, the ground claimed it. The 4 cylinders that Ford cut off, the difference between a V-12 and a V-8, were the difference between a failed aircraft engine and the finest tank motor of the war. Every engineer who worked on the V-12 was building something they believed would fly at 30,000 feet. None of them imagined it would spend its life crawling through mud at 15 miles per hour, carrying 35 tons of steel and 5 men who were trying not to die. It teaches that over-engineering is not waste, it is insurance. The GAA was absurdly overbuilt for a tank engine. DOHC with bucket followers, gear-driven everything, dual magneto ignition, forged aluminum pistons, aircraft-quality materials and tolerances in a ground vehicle that would never exceed 2,600 RPM. This over-engineering meant that the engine operated well within its design limits under even the most demanding combat conditions. The result was reliability that no other tank engine could match, not because Ford designed for reliability, but because Ford designed for performance that was never fully utilized. It teaches that mass production is a weapon. Germany built excellent engines. The Maybach was a competent design, despite its flaws. But Germany could not build them fast enough, or maintain them reliably enough, or supply spare parts consistently enough to keep its armored forces operational. Ford could. Ford built 27,000 GAA engines at a single plant in Detroit, using the same mass production methods that built Model Ts and flathead V8s. The German approach was craftsmanship. The American approach was industrial scale. In a war of attrition, scale wins. And it teaches that engineering outlives the purpose for which it was created. The GAA was built to win a war. It did. Then it powered irrigation pumps and logging equipment and oil field machinery for decades. Then hot rodders discovered its untapped potential and pushed it to 3,000 horsepower. Then, 74 years later, Ford introduced a production sports car with a flat plane crank V8 and DOHC valve train and called it a breakthrough, using the same architecture that the Lincoln plant had been stamping out in 1942. The Ford GAA is the greatest V8 most people have never heard of. It was born in anger, built in haste, installed in a tank that history remembers more for its weaknesses than its strengths. But the engine itself had no weaknesses.
It was and remains a masterpiece of mechanical engineering, the accidental offspring of a rejected airplane motor and the most productive automobile factory on Earth. The next time you hear a Ford V8, in a Mustang, in an F-150, in a GT supercar, listen. Somewhere in that sound, buried under 80 years of refinement and evolution, is the echo of the Lincoln plant in 1942, the echo of a 1,000-cubic-inch Kank motor turning over for the first time, the echo of Henry Ford, furious at Rolls-Royce, building something better out of spite. The engine that nobody wanted became the engine that everybody needed. That is the Ford GAA. That is American engineering. That is how you win a war.